My name is Gift Matebula and my student number is T447573.
My name is Bumuzi Dlamini. My student number is 2371813.
Hi, my name is President Lowe. My student number is 2369758.
Hi, my name is Nitanda Kachero. My student number is 261078.
This is our project we're going to be doing for 3 weeks.
A hydroelectric power generation system is a sustainable method of electric generation whereby the power of water and gravity is harnessed to produce electricity. The textbook problem that our group used was obtained from the fluid mechanics textbook by Frank White, specifically problem 3.135, where two reservoirs are positioned at different heights and the turbine located below allows the water to flow from the higher reservoir to the lower reservoir, resulting in electricity production. Our assumption that we have made is that we will use 88% efficiency due to frictional losses that occur as a result of the rotary motion of the pump turbine. The objective of the project is to construct an hydroelectric power generation system whereby the experimental, theoretical, and numerical models of the system will be utilized to validate the accuracy of the experiment.
The apparatus that were used for this experiment were glue gun, glue sticks, paper straws, plastic straws, bottles, takeaway, and pump turbine that was created using straws. And on methodology, we used a bottle to create it as the upstream reservoir. Then the takeaway was used to create a downstream reservoir. An upstream reservoir had to be placed in a place of higher elevation so that we could harness a higher hydraulic potential energy. Like in practical relevance, this experiment is basically used to convert hydraulic potential energy to mechanical rotational energy, then to electrical energy, which means this conversion of energy is basically used to light bulbs, LED bulbs. The type of apparatus used also played a role. For example, when we were using the plastic straws as the pipe with a plastic straw with a smaller diameter, there was a lower flow rate. This was due to the effect of diameter, which means the larger the diameter, the higher the volumetric flow rate, which results in the higher rotation of the pump turbine. This statement could be supported by the video, as seen on the video. When we used a paper straw with larger diameter, it resulted in a larger flow rate, and that thing was rotating. The pump turbine was rotating strongly.
If one side is pushing and the other side is just rotating. Yes.
They didn't say 10%, never mind, still high.
No, this thing is leaking. Don't mind the leaking. Now we put that system.
This is Bumuzi Dlamini talking about the FlowNext simulation. Our FlowNext model consists of 4 components, namely the pipes, the upper reservoir and the lower reservoir, and the pump. The assumptions for the simulation were that the roughness is 0 And one end of the pipe is located at the lowest point of the upper reservoir, and the other end is located at the highest point of the lower reservoir. The pump is used to denote the turbine, which converts kinetic energy to electrical energy. After the simulation, graphs of the water levels of both the upper reservoir and the lower reservoir were drawn, and the graph of the power produced was drawn. The power showed a parabolic decrease, and so does the flow rate as with time.
The time it takes to empty the upper reservoir using the experimental and numerical method is compared. It takes 62.02 seconds to empty the reservoir in an experimental setup, whereas it only took 46.46 seconds to empty the upper reservoir in the numerical simulation. This indicates that frictional losses do play a significant role as they were neglected in the numerical simulation. We then concluded that the experimental and the numerical methods show the difference between the two methods is like we can approximate it to be 25% based on the assumptions made. It can be concluded that the numerical method can be used to validate like our experiment.
Yeah, sure.
No, it's still 8.